In this video, we're going to take a closer look at the concept of the magnitude of a vector. We kind of referred to it in an intuitive way when we defined a vector, but we didn't really talk about how do we compute the magnitude of a given vector. And that's what we're going to do now. Let's start in R2. And just for convenience, let's say we have a vector with initial point at the origin. We saw previously that you can have equivalent vectors with lots of different initial points and therefore different terminal points. But here, let's just assume that the vector starts at the origin and then it goes to the point x1, y1, right? So, and that's our vector. So that means this is x1 and this is y1. So we're going to call that vector v, and then from previous work we know that v can be written in component form as x1 comma y1, right? Now the magnitude. Well, what we're going to use to represent the magnitude of this vector is the length of the line segment. Remember, a vector is a directed line segment. So we define the magnitude of v, right? And here's the notation that we're going to use for the magnitude. We're going to use these two, like these double bars. They look like double absolute value bars, right? But so as not to confuse them with the absolute value, we're going to double them up, right? So this is the notation that we will use for the magnitude of the vector, and the way it's defined. So the magnitude of the vector v is, or let's say define it as the length of line segment OP, right? So that means we know how to find the magnitude of the vector because we know how to find the length of a line segment. So let's write down the formula. So in this case, the magnitude of this vector with components x1 comma y1, looking at the triangle, right? Looking at the triangle, this length being x1, this length being y1, then when we apply Pythagoras, it will be the x value squared plus the y value squared, and then you take the square root of this, right? So this is the famous formula for finding the magnitude of a vector in R2. And the computation is exactly the same in R3. So similarly, if V is the vector x1, y1, z1, right? So if it's now a three-dimensional vector, right? And we can state that clearly. So if that's a vector in R3, then the magnitude of this vector is equal to the square root. So square the x component, add to that the square of the y component, and add to that the square of the z component, right? So really straightforward to find the magnitude of a vector. Let's just do two quick examples. So if, let's say, v is the vector -2, 3, then its magnitude, so how big or how long is this? So the magnitude of v is -2 squared plus 3 squared, and then we take the square root of that. So that gives us the square root of 4 plus 9, So V has a magnitude of root 13 units. And then similarly, let's pick a vector in R3. So let's say we have the vector 2, 3, 6. Then its magnitude, so the magnitude of W, is the square root of 2 squared plus 3 squared plus 6 squared. So that's the square root of 4 plus 9 plus 36. So that's the square root of 49. And hey, 49 is a nice perfect square. So we get a nice integer magnitude, right? Now, when referring to the magnitude, again, we've already defined it as the length, so sometimes you might use the word length, but there's another word that's also synonymous with magnitude. So here are three words that represent the same thing. So magnitude is equivalent to length. And then there's another mathematical term that refers to both of these, and it's called the norm, right? So you have the magnitude of a vector, the length of a vector, the norm of a vector. They all represent the same quantity, right? Now, so again, finding the magnitude of a vector, pretty straightforward. Now, if the magnitude, so if the magnitude of V happens to be equal to 1, right, then this is a special kind of vector, and we refer to it as a unit vector. The word unit referring to the number 1. So if the magnitude of V, or the length of V, or the norm of V is equal to 1, V is called a unit vector, right? For the unit representing 1. Now, there are lots of vectors that have a magnitude of 1, but there are some really special ones that allow us to represent vectors in a slightly different way. So let's start in R2. There are two what we call standard or basis vectors in R2. So here we are in R2. And here are the two vectors, and I'll draw them in red. So the vector that starts at the origin and goes to the point 1, 0, right? So that vector will have unit length, right? And then similarly, starting at the origin and going to the point 0, 1, so this vector is also a unit vector. And these are called standard unit vectors, and they have a special notation. The vector that goes from the origin to 1, 0, this is the vector I. And the vector that goes from the origin to the point 0, 1 is the vector J, right? So let's write this down. So I would be the vector 1, 0, and J is the vector 0, 1. So these two vectors are called, so our standard unit vectors in R2, right? And now why are they important? Well, it turns out with these two simple vectors, 1, 0, 0, 1, these two nice binary vectors, we can express every other vector in R2 as what we call a linear combination of I and J. Now, what do we mean by linear combination? And again, this is something that you go deeper into, like in a linear algebra class, but I'm just going to explain quickly what a linear combination is. you are allowed to scale these two vectors by any constants you want. So you can multiply this vector by any constant, this vector by any constant, and then add the results together. So you can use the two standard arithmetic operations for vectors, scalar multiplication and addition, to combine these two. If you are allowed to do that, you can create every vector in R2. In fact, let me show you how it works. It sounds scarier than it really is. So for V, and then what I'm going to do is I'm just going to write V as, let's say, V1 comma V2. So for this vector that's in R2, this is how I can express it in terms of I and j. So I can take my vector v, and again, remember what the components of the vector represent, right? The components, they represent the change in each of the different directions. So this tells me that there is a v1 change in the x direction and then a v2 change in the y direction. In other words, I can write this single vector as the sum of two kind of simpler vectors by saying v1 comma 0 is one vector and then plus 0 v2. So it's almost like I can decompose this single vector into the sum of these two vectors. This is the vector in the x direction. Notice there's no change in y. And then this is the vector in the y direction. Notice that there is no change in x. Okay. And then what I can do, I can actually do the reverse of scalar multiplication. And let's factor out the v1 out of the first vector. So v1 times 1 comma 0. And then plus factor out the v2 out of the second vector. So put your v2 outside and then 0 comma 1. And then look at what you have now. This is your I, right? So this is I and this is j. So we can express the vectors in the component form using the angle brackets separated by a comma, or we can express it in this other form where it's v1 times I plus v2 times j, right? So now we have an alternative form of representing vectors. So for instance, again, just an example. So the vector, let's say 10, negative 20, may be expressed as, so now I could say this would be 10i, let me write it like this, plus negative 20j, or I could just write it as 10i minus 20j, right? So now using these, so this is like our standard unit vector notation, and this is the component form of the vector. It's telling us the same thing, right? Just in a slightly different way. Looking at this, it says, yeah, 10. So assuming that the vector starts at the origin, well, actually, it doesn't even matter where it starts. But this vector goes 10 units in the positive x direction, and then 20 units in the negative y direction. So just looking at this, just like how you could do it the same way looking at the component form, we can tell exactly what the vector does. And unsurprisingly, there's a way that this can be done in R3. So there are 3 standard unit vectors in R3. And let me draw our coordinate system. Right, and again, we know what this, so we have our x, we have our y, we have our z. So now what are these special vectors? So Again, they all start at the origin, the standard ones, and they're going to go 1 unit in each direction. So that's going to be 1, that's going to be 1, that's going to be 1. And we're not going to change what we have in R2. This one along the X, in the X direction is I. This one in the Y direction is J. And now we need a new one, another one, a third one in the Z direction, and this is K, right? So here we go. So we got I, and this is in R3, is the vector 1, comma 0, 0. So this vector lies entirely along the x-axis. And remember that this is consistent with what we stated earlier about properties of points in R3. That when the y and z are both equal to 0, right? Then the point has to be along the x-axis, right? And in this case, the vector here now lies entirely along the x-axis. And then similarly, J is the vector 0, 1, 0. This one is entirely along the y-axis. And then finally, our third standard unit vector in R3 is K, and that's now the vector 0, 0, 1. Again, these are binary vectors, right? These are binary vectors. And again, they all have magnitude 1. And then, so we can say for, if we have any vector in R3, so V1, V2, V3, then we can do the same algebraic steps that I showed earlier. So I'm just going to write it down. So this vector can also now be written as V1I plus V2J plus V3K, right? And then we can just for complete symmetry, let's do another example. So for example, let's say we have, I'll give it a different name. Let's say we have the vector W, which is -5, 1.2, and 1/3, right? Yes, you can have these nice fractional components as well. So this vector can be written as -5i plus 1.2j plus 1/3 k. Right? So just with this concept of a unit vector, which is a vector that has magnitude 1, then we can define these new standard unit vectors, and we have alternative ways of writing the, so we can still refer to this as the components, but here it's like the components are used to combine the I, the j, the k, and this is what we refer to as a linear combination, when you're allowed to multiply a vector by a scalar and then you can add the results together. So all these operations here will produce this single vector. Now, there is another important but simple operation that is related to the magnitude, and it's this. And in fact, let me kind of illustrate it with an example, and then we'll state the general formula. Suppose I have a vector that is like this, and here's the vector v. I'll give you the component form of it. So let's say it's 1, -2, 3, right? So there's the vector. So just the fact that it has 3 components, I know that this is a vector in R3. I don't need to draw the coordinate system for what I'm trying to do. And we can compute this, the magnitude of this vector. So let's compute the magnitude. So the magnitude of V, So I'll square the components, add them, and then take the square root. So it's 1 squared plus negative 2 squared plus 3 squared, and then we take a square root. So that's the square root of 14, right? So that's the length of this. But what if we wanted a unit vector, right? So what if we wanted a unit vector that acts in the same direction as v? So we want it to point in the same direction, right? But we don't want it to be root 14 units long. What we want it to be is 1 unit long. So what would that vector be? So the vector acting in the same direction, so pointing in the same direction, so acting in the same direction as v, right? But with magnitude 1 or length 1. So with length 1 unit is, well, so it's like we essentially want to break this up into units of 1, right? So since we know the entire length of this vector is root 14, if I were to take this vector and divide it by its magnitude, then essentially I would be forming a new vector that would be, let's say, here. But then this vector would have magnitude 1. And I'm going to call this one u, u for unit, right? So u in this case would be my original vector v. Let me write it like this. So if I take my original vector v and divide it by its magnitude, right? So I don't want it to have a length of root 14. Instead, I want it to have a length of root of 1. And this will give me that unit vector, and it's guaranteed to act in the same direction, right? Because it's really just going to be this multiplied by a certain scalar. In other words, this operation here where you take the vector and divide by its magnitude, you can interpret it as 1 over the magnitude of v times the vector. So this is the scalar, right? And then this is the vector. So we are doing scalar multiplication. So let's write down what the actual answer would be. So in this case, the unit vector is going to be 1 over the square root of 14 times, and this is my vector 1, negative 2, 3. So if I now do my scalar multiplication and distribute the 1 over root 14, I will get this vector 1 over root 14, comma, negative 2 over root 14, comma, 3 over root 14. And so we claim that this is a unit vector. Let's check that to see that it is actually a unit vector. Check. So if I look at its magnitude, well, what do I have to do? I have to square each of these components and add them together. So it's going to be 1 over root 14 squared plus negative 2 over root 14 squared plus 3 over root 14 squared. And you take your square root of that. So what do we end up with? So 1 over root 14 squared is 1 over 14 plus negative 2 over root 14 squared is 4 over 14 plus, now 3 over root 14 squared. That's 9 over 14. We already have a common denominator of 14. And the numerator, we also have 14. So there you go, root 1, which is equal to 1. And that's what we want, right? So the process of taking a vector like this, right, and dividing it by its magnitude, that process will produce a unit vector. So we're going to write down that formally, but there's something that we have to state before. And now, if v is not the zero vector, what do we mean by zero vector? Well, the zero vector is a vector where all the components are zero. So it really has no direction, right? And the magnitude would be 0. We have to avoid that because we can't have 1 over 0, right? Because since we're dividing by the magnitude, we have to make sure that that magnitude is never 0, right? So if v is not the zero vector, which means, so the zero vector is the vector where all components, so where all components are equal to 0, as long as we don't have that, then the unit vector acting in the same direction as v, or pointing in the same direction if you want to say it that way, acting in the same direction as v, not of v, let's say as v, is given by, so I'll use u for unit, and what do we do? Well, again, it's 1 over the magnitude of v times v, right? And if v is already a unit vector, then yeah, the magnitude would be 1, so you'd have 1 over 1 times itself, so it wouldn't change. If it's not a unit vector and not the zero vector, then you can do what, and this process here is called normalizing. So this is called normalizing v. So this is called normalizing v. And it's an important step. It's a simple calculation, just dividing by the magnitude, but it's a calculation that will be a part of bigger problems that are yet to come. An example where we will go through this particular process. So let v be the vector, and I'll go ahead and use our new notation, 2i plus 2j minus k. So let's do this. Let's say, let's part A, find the vector that is twice as long, so twice as long as v, acting in the opposite direction of v. Right? Well, how would we do that? Well, So opposite direction, so we know that there's going to be a negative involved, and we want our new vector to be twice as long as this vector. So the answer to this really is given by negative 2v. That's it. The negative takes care of the opposite, and then the 2 takes care of the twice as long. So this is negative 2 times 2i plus 2j minus k, and that's the vector negative 4i minus 4j and then plus 2k. All right? Let's do a part B. Let's say find the unit vector acting in the same direction as v. Right? So find the unit vector acting in the same direction as v. Well, for that we have to normalize it, right? So unit vector, we want the length to be 1, and we want it to be in the same direction, so no negative. So it's simply going to be 1 over the magnitude of v times v. Well, let's see what the magnitude is. So looking at v, it's 1 over, and then we'll have 2 squared plus 2 squared plus negative 1 squared, all under a square root, times v. So 2i plus 2j minus k. And this is the, so what do we have? We have the square root of 9. So this is 1 over root 9 times 2i plus 2j minus k. So that works out nicely. We're going to end up with 1/3, and then distribute the 1/3 to get 2/3 I plus 2/3 j, and then minus 1/3 k. Right? So this is a unit vector that points in the same direction as v. And then let's do part C that says find the vector of length 10 acting in the same direction as v. So acting in the same direction as v. Well, let's think about it. The unit vector, it has length 1, and acting in the same direction of v is this. So all I would have to do is take my desired length, which is now 10, and multiply the unit vector, right? So the answer for this is going to be 10 times 1 over the magnitude of v times v. So it's essentially take the unit vector and multiply it by whatever length you want. So the unit vector, we know this is the right direction, right? We know it has length 1, and if I multiply it by 10, the resulting vector will now have a magnitude of 10, right? So it's basically taking our answer from part B and multiplying it by 10. So we're going to again do our scalar multiplication. You see how many times we end up multiplying a vector by a scalar. And then we're going to end up with 20 over 3i plus 20 over 3j minus 10 over 3k. And then, again, there's no particular reason why I'm using ijk, just to kind of get more practice using this new notation for our standard unit vectors. And there we go. So that's our example. It required us to use our magnitude formula in part B, and then there are several times where we had to do scalar multiplication. So hopefully you found that interesting, and I'll see you in the next video.